How about now? Is it
Yeah,
recording?
it's recording again.
What did you do? You looked at it funny. You guys got to give it the warm, fuzzy thoughts. So, okay. So I'm solving for x. So x is a fourth p. Okay. Now, the mistake most people make in Calc 1 is they assume, oh yeah, so obviously I'm going to have a maximum. Obviously I'm going to have a minimum. Aren't there three possibilities? I could be this, I could be this, I could be this. Right? Think simple graphs. There's three different ways I can have a horizontal tangent. You don't automatically assume it's the thing you're looking for. You got to actually show it. So you have the first derivative test. That's where you set up the intervals of increasing, decreasing, and decide, did I go from increasing to decreasing? Did I go from decreasing to increasing? There's the second derivative test, which is actually the easiest one because this is a polynomial. And that's what, am I concave up or am I concave down where I have a horizontal tangent? And then the third one, which is my favorite, is what's called the extreme value theorem. If you have a closed interval, then the extrema must come from either the critical value or the endpoints. You guys remember that one? And that one was, all of them were really easy to use. So in this case, let me use the extreme value theorem. Now, x. Can x be any real number? Or does x have a limitation? Certainly, can x be negative? No. I mean, it would be kind of a boring fence, but technically, could x be 0? I give you two really long slats and I put them next to each other. That'd be a terrible dog run. But does it violate any laws of physics to have 0 area? No, it'd be a terrible idea, but there's nothing wrong with that. What's the most x could be? Well, think if y were 0, what would x be? 1/2 of the perimeter. Oh. So by the way, it doesn't make any sense to use either one of the endpoints because that means we'd have 0 area. But like I said, it doesn't violate any rules. It's just a really bad idea. Because if you say, well, no, you can't have 0 area. So let me make one of these widths, you know, 1/2 inch. Now I have a rectangle. It'd still be a bad choice, but in other words, it's not impossible. So what we did was we said, what's a of 0? What's a of 1/2 p? And what's a of 1/4 p? The biggest one wins. This is the extreme value theorem. Well, we already know what the biggest one's going to be because both of these are going to be 0. And this will be what? If I put a 1/2 p in there, excuse me, a 1/4 p, I'm going to get 1/16 p squared. If I put that in there. Okay? So that means, let's see, if x equals 1/4 p gives me the maximum, then what would y have to be? So if I go in and calculate, let's see, y was 1/2 p minus 1/4 p, which is, oh my gosh. The maximum area is going to come from a square. Gee, what an epiphany, right? You never saw that one coming. No, you guys you knew that was going to be the answer ahead of time. But how do you show it mathematically? We just did. So in optimization problems, you're saying what situation gives me the best or worst? Because I might be looking for the minimum. A similar question, by the way, would be, I have this much area to use. In other words, I'm giving you flooring material maybe. I'm giving you tiles. I have this much area. I want to minimize the perimeter because I want to minimize the cost. I'm giving you the area. I need to construct a room that has 100 square feet. So I'm giving you 100 1x1 tiles. Could you line them up all in a row? Sure, but that'd be the most amount of perimeter. I want to minimize my perimeter, and then we discover similarly that would be a square. Again, so if given the area, the square minimizes the perimeter. Given the perimeter, the square maximizes the area. Oh, okay, so there'd be different goals. But in either case, we just did an optimization problem. Now we have so many types of problems that we did in Calc 1, but our limitation was the same as everything else. We can only do it with one variable. What if I have more than one independent variable? I'd like to do the same problem, but now we need a completely different way of doing it. And we will come back to this problem. Now, I'm going to give you an example of something you did in baby algebra that wasn't that dissimilar. Okay, in remedial elementary algebra. Some people call it 9th grade algebra, although it became 8th grade algebra a number of years ago. Algebra 1. Okay, at the theater, they sold 1,000 tickets. Child tickets cost $8, adult tickets cost $12, and the total revenues for the day were $9,768. How many of each kind did they sell? Do you remember doing problems like that? So you said, okay, let X be the number of adult tickets, then 1,000 minus X would be the number of child tickets. Then if I multiply the adult tickets by the cost, and you did all this and you set it up, and you solved it, okay? Then you get to algebra 2, intermediate algebra. And now you do the problem differently. You say, no, let X be the number of adult tickets and let Y be the number of child tickets, and then X plus Y is 1,000. And then it's so much easier to set up. But we didn't do that in Algebra 1 because we did not learn how to solve 2 variable problems in Algebra 1. We only learned how to solve 1 variable problems. But the moment I allowed that to be a 2 variable, now I give you 2 equations and 2 variables, and now I get to use a whole bunch of different methods. You know, the addition method, substitution. But for most people, understanding the problem was easier with 2 variables. But isn't that a higher level of reasoning? I mean, solving a 1 variable problem is easier. A 2 variable problem, I have to make it into a 1 variable problem. But the statement of the problem was way easier when I was allowed to use 2 variables. So why did we make that switch? Because now it's, I've got $1.37 in my pocket. I have 14 coins. Some of them are pennies, some of them are dimes, and some of them are nickels. And I have twice as many nickels as I do pennies and 3 times as many dimes. I just gave you a 3 variable problem with 3 equations. If I can solve the 2 variable problem, then I can use the same sort of reasoning to solve the 3 variable problem, and then eventually introduce a matrix and things like that. That's why we had to up the ante. That's why we had to increase the way, level of difficulty in the way we did it. That problem with the theater, you never had to make it a 2 variable problem. But if I don't make that a 2 variable problem and learn how to solve that one, I'll never be able to solve it when there's more than 2 variables. You understand? So this problem could have multiple independent variables. It could have 3 independent variables in the end, and we need that method, which will be completely different. You don't use a matrix to solve a 1 variable problem. So let's go back and quick reminder of something we've already done. All right? I've got some function, my constraint, we're going to call it. I have to be on some curve, right? Y equals f of x. So what did we do? We said f of x minus y equals 0. We'll call that our new function. Right? We've been doing this now for a couple of weeks. That's not new. All right? Everybody go with that. We did this. And then we showed, I did this one already. I said, well, let's consider just sort of a general. Let's call that r of t. Okay? Then if I said, well, let's make x of t, and y be y of t, then r of t is much easier to describe, right? R of t is then what? X of t, y of t. I like doing that better, so much easier. And then what we showed last day was if I took the, different colors here, at any particular place, if I took the normal vector and I took the tangent vector, well, I know the tangent vector is r prime of t. And what did we show the normal vector was? You guys remember? It's kind of important you just turned in a quiz where you used this. Give you a hint. It starts with a g, ends with a radiant. Oh, good. The gradient vector, right? You guys remember we showed this was the gradient vector? How did we show this was the gradient vector? Well, we said if I rewrite g as g of x of t, y of t, and now I want the gradient of g with respect to t. I want to remind you because we're going to use this today. Then what would have I got? I got the partial of x, excuse me, the partial of g with respect to x, sorry, times dx dt, plus the partial of g with respect to y times dy dt. I don't need this anymore. Which we noticed was, hey, this is exactly the same as a dot product. I'll remind you, we made this discovery, I don't know, 3 classes ago. And this we know is therefore, that is the gradient of g, and that is the RDT. Okay, great. So why is that important? Because I'm differentiating something that's already equal to 0. And that's the proof that the gradient vector is orthogonal to the tangent vector. That's why the gradient vector is the normal vector. Now, when we talk about a normal vector, is its length important in general, or just its direction? Yeah, because if I said go that way, it doesn't matter how, go that way. It's the direction. Earlier in the semester, we made it into a unit vector. We don't need to do that anymore. We don't need to make it into a unit vector, but we understand that it's all about direction. So this is cool. I'm restating something we already know, because now I'm going to introduce a new piece of the puzzle. This is at any place on the graph. Now let's suppose, hypothetically, that I have some function f of x comma y, nothing to do with the picture. I have some function and I want to find its extrema. Either its max or its min, in some cases maybe both. But I just want to find an extrema. Find the extrema, sorry, of some function. The function is unrelated to the picture. It's sort of like in the last one, I want you to find the maximum of the area given the constraint. The constraint was I had to be on a rectangle. Okay? So I wanted to maximize x times y. X times y didn't have anything to do with the picture. The picture was the thing that was the constraint. So I want to maximize or minimize this subject to this. I still have to be on the curve. So whatever the answer to the question is, it has to come from the curve. You understand? What did you do last day? I gave you a function of two variables. I said, consider f of x, y. Now find any extrema or saddle points. But wasn't your domain the entire xy plane usually? Is my domain the entire xy plane here? Of potential? No, it's only the points on the curve. That's pretty restrictive, isn't it? Oh, so if I just simply said, forget the picture, find the extrema of this. This is straight up last day's lecture. Okay, take the partials, set them equal to 0, use the Hessian to figure out if it's max, min, saddle point. Great, that's what we did last day. Okay, but now that's not what I'm asking you now. Now I'm saying, no, I want you to find the max or min, but it has to be on the curve, period. Okay, that changes everything. That makes it much, much different. Because what if the max or min occurred way over here? No. So let's suppose that there is a place on the curve. Let's suppose there is an answer. Hint, 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 there's always going to be an answer. And let's suppose the place is, sorry. I already know what that is. Let's say it's right here. Let's say this point here is x naught, y naught. There is a particular point on the curve that gives me the extrema. So f of x naught, y naught is the extrema. Remember, extremas are the z values. Let's suppose there actually is one. Now, whether it's a max or min is not important yet. It's an extrema. The problems that we did last day, you didn't know if it was a maximum or minimum before you started, right? You tested it later. You did the Hessian and said, oh, you know, positive, negative, that kind of stuff. So let's suppose, so what is this vector? This would very specifically be r of t naught. Okay? Now, x naught is x of t naught. Y naught is y of t naught. That's not new. That's how we get that. So what I want to do is restate my f function, because I want to make it a function of t. So let's let capital F of t be f of x of t, y of t. I don't have a function of t. I just said maximize or minimize f of x, y. But I'm now going to make it a function of t so I can use that position vector. It's kind of clever. Now, if x naught, y naught is the place that the answer is going to come from, that's my critical point, f of that is my extrema. Remember, critical point is the input, extrema is the output. Then f prime of t naught should be what? The derivative of this, I'm going to write it like this. Evaluated at t naught. There's really no clean notation there. And what will that be? That will be 0. Why? Because that's where my extrema occurred. Remember, extrema is going to occur where the derivative is 0. Agreed? But part of the reason I wanted to make it a function of one variable, it's easier to state the derivative. Now, there's going to be partials, we know that. So I'm starting with the assumption that I do have something happening at x naught, y naught, which is the same as saying something's happening at t naught. Okay, so let's go back to here. Tell me exactly what is what is f prime of t? No, that's awful. Try that again. What is f prime of t? There we go. Look at that. Well, wouldn't it be the partial of f with respect to t, with respect to x, times dx dt, plus the partial of f with respect to y times dy dt. Okay, great. You getting a sense of deja vu here? Have you seen this before? Doesn't it kind of look like what we just did over there? Now, f and g have nothing to do with each other. F is the function I'm maximizing and minimizing. G is the constraint. In other words, I have to be on that curve. I could give you, I'm going to give you an f of xy. One f of xy. How many curves could I possibly come up with? Infinitely many. I'm only going to give you one f. There's an infinite number of possible curves. The curve is the constraint. Actually, for a different f, for the same f, let me give you a different curve. Let me give you a different curve. Let me give you a different curve. I'm always going to get a different answer, but I'm maximizing or minimizing the same f. Each time I produce a new g, it's a different constraint. But this looks like the other thing. This looks like this. Doesn't it? Okay. And that clearly is the gradient of f dotted with dr dt. Okay, well, that's not really that interesting. That's just a dot product. Except for the fact that, by the way, this is true in general. This is not equal to 0 in general. Where is it equal to 0? At the critical point. So it's equal to 0 when I'm at x naught, y naught, or t naught. Oh, so if I said f prime of t naught, then what I've got is this is equal to the gradient of f. Now, my little f, you could say it like this, at x naught, y naught. Because that's the way we define little f. Dotted with what? dr dt evaluated at t naught. I'm going back and forth because little f sees x's and y's. And what does all this equal? 0. So here's the key. No matter where I am on the curve, the gradient vector is going to be orthogonal to the tangent vector. Everywhere on the curve. We know that. My f of x, y has an infinite number of possible values on this curve. That's great, but only one of them can be the max or the min. We'll just assume that. There are situations where I might have more than one, but let's assume there's going to be one for now. So if I just took a random point on the curve, that's not going to be a max or a min. And when I restated this, f prime of that value is not going to be 0. I only want the one where f prime is 0. We call that t naught. So at the place that you have your extrema, this dot product is 0. And that's why this is really cool. All right? Now let me ask you a real simple question. We'll keep it really simple. And by the way, neither one is the unit vector. I'm not talking unit vector. If u dot w equals 0 and v dot w equals 0, and let's assume none of these are the 0 vector because it doesn't change the results, by the way. But conceptually, it kind of messes you up. U is orthogonal to w, v is orthogonal to w. Tell me about u and v then.
Parallel.
The parallel. And parallel vectors simply means they are scalar multiples. Isn't that cool? So tell me about the gradient of g and the gradient of f. They're both orthogonal to the tangent vector. That means they're scalar multiples. Parallel vectors, this is what's weird. Parallel lines never intersect, so they can't be scalar multiples. So why do we say parallel vectors are multiples? Here's the simplest explanation I can give you. We're gonna have the first ever Math 252 Olympics. And we're all gonna run the 100 meters if we can do it. So you got a whole bunch of lanes. Right? So you're next to me, Jamie, right? You're next to me, you're next to me, and we all run. Aren't we running parallel? Yep, and we're all running along a vector, but when we take our vectors and put them at the origin, won't they all look like the same vector? In other words, parallel in space, when you put the vector oriented at the origin, will be the same vector, won't it? Oh, because it's coming out of the origin. That's why we say parallel lines produce vectors that are scalar multiples. That's why, because we always orient the vector back to the origin. So even though the lines themselves are parallel, the vectors were multiples. So that's when we say, quote unquote, parallel vectors, that's what we mean. They're multiples. They're going in the same direction up or opposite directions as scalar multiples. So the big picture here is then that the gradient of f is equal to some scalar multiple of the gradient of g where the thing happens. And the symbol we use is the Greek letter lambda. Make sure I spell it right. It's the Greek letter lambda. And lambda is called the Lagrange multiplier. It's a scalar. It's not a function. Now the funny thing is, when we do these problems, we're not actually interested in finding the value of lambda. Sometimes we get lucky and lambda's just sitting there. Oh, lambda is 3. Most of the time, we don't even care what lambda is. We use the relationship that they're multiples. That's where the lambda will come in. So the idea of this is, I'm going to give you a function of 2 variables, and by the way, we'll also work with more than 2. Let's concentrate on 2 for now. I'm going to give you a function of 2 variables and ask, are there any extrema over the whole xy plane? Maybe there's not. Maybe there's something that's just always going uphill. But now if I said, I'm going to give you a constraint. Now from Calc 1, we know when we had a closed constraint, there absolutely was a maximum and a minimum. In fact, there was an absolute max and an absolute minimum. They had to come from critical values or endpoints. You remember that? Oh, okay, that's the extreme value theorem. Now I'm giving you a constraint. Now the constraint may not be finite, but if I have to stay on the constraint, what we're saying is, overall, there might be a maximum or minimum on the xy plane, but it's irrelevant if that point isn't on my constraint. So I only want the value on the constraint. The constraint's going to produce an extremum. It isn't necessarily going to produce a maximum and a minimum, but it will produce an extremum. We will be able to figure out if it's a max or min, and I'll show you that one. That's actually the easiest part. Kind of like when I was talking last day about determining if something's local or absolute. It's actually quite easy. Is it going up or is it going down forever? Well, determining if it's a max or a min is actually quite simple because I just look at the right thing. I'll show you what that is. So let's go back to the problem we started the class with. I want to maximize area is a product of x and y subject to 2x plus 2y equals p. P being a constant. This is the problem we started class with. This was a 1 independent variable problem. But now I want to treat it as a 2 variable problem. So this is my f of xy right here. Now I need a g of xy. I need to write my constraint as a function of x and y. Well, I think we know how to do that. Why don't we let g equal what? 2x plus 2y minus p. Remember, the way you create your constraint is throw everything on one side and have it equal to 0. So now I want to maximize this product subject to this. Okay, let me rewrite that as g of xy. Okay? So we're going to take 2 gradient vectors and then we're going to set them equal with a lambda in there somewhere. To make it consistent, let's call this f of xy, just so we use the same notation. What is the gradient of f?
Y, comma x.
What is the gradient of g?
2, comma 2.
Does everyone agree with that? So the Lagrange multiplier says that this vector is lambda times this vector, or if I write it this way, y comma x is lambda times 2 comma 2. Well, that gives me 2 really simple equations. Y equals 2 times lambda, x equals 2 times lambda. Boy, solving for lambda is going to be real difficult because I don't know what x and y are. Well, why would we want to solve for lambda? We're trying to find x and y. If x equals 2 lambda and y equals 2 lambda, can you make any really humongous conclusions? How about x equals y? Because they're both equal to 2 lambda, and we're basically done. X equals y is the result that the Lagrange multiplier told us. Okay, so if x equals y, now I can figure out, by the way, I don't have any values to do it. I need values for x and y. Where do I get the values? From the constraint. So if x equals y, and I put them both in the constraint, then I'm going to get x equals y equals 1/4 p. We know that's what we're going to get. So what I would do is, I would go back to my constraint and say, well, let me replace y with x. Now I have 4x equals p, so x is 1/4 p, therefore y is 1/4 p. Now, this is going to produce an extrema. How do I know if it's the max or the min? This is the easy thing. It has to be either the max or it has to be the min. You don't make an argument, you test any other solution to the constraint. So go back to your constraint. Give me anything that satisfies the constraint. Okay, how about 1/2 p, 0? Would that satisfy the constraint? And so here's my test. The area, when I put 1/4 p, 1/4 p, is 1/16. We did this before, right? P squared. Pick any possible x, y that satisfies the constraint. So I'm going to test, I just said, x equals 1/2 p, y equals 0. I'm going to test that one because that satisfies the constraint. So the area of 1/2 p, 0 is, of course, 0, which is, by the way, very important to state, smaller than 1/16 p squared. Therefore, this produces the maximum. Your test is always the same. You pick anything that satisfies the constraint, put it into the function that you are finding the extreme of, the function you are either maximizing or minimizing. If that value is greater than your answer, then your answer is the minimum. If that value is smaller than your answer, then your answer is the max. That's it. Now go back to Calc 1 for a moment. How did we define an absolute max or min? It's the absolute max if it's greater than every other y value. So all you had to do was test another y value to see if it was bigger or smaller. And that gave you the answer. Yeah.
Don't you have to test both endpoints? Just test both endpoints?
No, you take anything that satisfies the constraint. Is 1/2, 0 the only thing that I could use? What if I just, be goofy? How about if I used a 3rd p and a 6th p? That would work, wouldn't it? Take any x and y that satisfies this. There's an infinite number of possible answers. I'm going to pick one. I always like using as many zeros as I can just because it's algebraically less. Okay? Everybody cool with that? All right, let's do some examples. Oh, here we go. I printed some. I'm really terrible at making this stuff up off the top of my head. But this stuff is so powerful. There's so much you can do with this now in reality, because now we have the means to find extrema in 3 dimensions subject to constraints. We could not have done this any other way. Okay, what we did last date doesn't apply to this, because that's when I have the whole xy plane as my domain. Okay, so let's find and I'm going to put any extrema because it's possible you could have more than one. There are occasions when you actually can get 2. Not very often, though. Of f of xy equals 2x squared minus 4y squared, subject to, I got to be on the plane. Okay, now that constraint is just a line, isn't it, technically? But in 3 dimensions, it would actually be a plane. But I got to be on this, so my domain, my xy plane, this is a line. That's very restrictive, isn't it? I have to be on this line in order to make.
Is the storage full?
Shouldn't be. I clear it out pretty regularly. Boy, I hope this doesn't really mess up our video. I had a class a couple days ago where I'd never heard it beep. but it ended up, when it was all done, it did 3 different sets of recordings. So I told you it does the 17.5 minutes, but it did 3 different labelings. Usually it's all the same labeling, 17.5. It did it as if it was 3 different days. And so trying to get them in order, it took a lot of work I had to rearrange them within the camera. It was, and I think as a result, it was, I think, the linear algebra class. There's actually a little blip in the middle somewhere, maybe like a 2-second blip. It worked out okay, but it was the first time they had done that, so hopefully it's not an issue. Now, I have my f. I'm finding the maximum or minimum of this, period. I could make up an infinite number of constraints, but I'm still doing this f. Every time I change the constraint, it would change the final answer. Does that make sense? So for this particular constraint, well, I need to create a function of x and y. So we will let g of x comma y equal, now just make this all equal to 0. The easiest way, 4x plus 6y minus 12. There's my constraint. The majority of the problems, you're going to find that the algebra is actually quite simple. Okay, the algebra is not going to trouble you most of the time because the functions you're working with are not going to be terribly complicated. You're going to see mostly polynomial-ish stuff. Not a lot of sines and cosines and exponentials, just because we missed the point. We won't be able to finish the problem in a lot of cases. So, the order of things. Let's start by identifying the gradient of f and the gradient of g. So what's the gradient of f?
4x.
And negative 8y, good. And the gradient of g?
4, 6.
Do we all agree with that? Now, the next thing you do, you can go directly to your equations. Does it matter which side you put lambda on in actuality? If they're scalar multiples of each other, does it really matter which side you put the lambda on? No, but if you were solving for lambda, if you put on the other side, it'd be the reciprocal. Lambda cannot equal 0. Because if lambda equals 0, then you'd never get an answer to any question. Or the flip side is you'd get every point on the constraint as an answer to every question. No, lambda can't be 0. Okay? So I could write this then as 4x equals lambda times 4, and negative 8y equals lambda times 6. Okay? In that statement, I'm not going to be able to solve for lambda. But can I create an equation involving just x and y? Yeah. What does lambda equal? X. Over here, what does lambda equal?
X. Wow.
Negative 8, 6, y.
So how about negative 4/3 y? Do you all agree with that? Therefore, what's my relationship between x and y?
X equals negative 4.
Yeah. I never found the value of lambda. Now, when we find the values of x and y, could we go back and determine the value of lambda? Sure. Will we ever need that to answer any question? No. We needed lambda to create the relationship between x and y. Now, here's this kind of interesting. Lambda is an unknown, isn't it? So don't technically I have 2 equations and 3 unknowns? You linear algebra folk. Do I get a unique solution if I have 2 equations and 3 unknowns? No, but I don't have 2 equations and 3 unknowns. I have 3 equations. 1, 2, 3. Your constraint is the other equation. See, in other words, how am I going to find the values of x and y? I'm going to take these, put them in here. Oh, then I'm going to get one answer. I'm going to get a unique solution. So, how about if I replace the x with negative 4/3 y? So then I'll have 4 times negative 4/3 y plus 6y equals 12. Okay, so far so good? So negative 16/3 plus 6, well that'd be what? 2/3 y equals 12, so y is 18. If y is 18, then what's x? Because x is negative 4/3 y, so x would be what? Negative 24? Well, we've done all the heavy lifting. F of negative 24 comma 18 is, use your calculator, this is what value? You can put it in here. Probably I don't know. Actually, don't even know if it's negative or positive. It's probably negative. Yeah, I think it's negative. What do you get? Anybody?
Negative 144.
Everybody agree with that? Anybody else get that? Okay, good. That means it's. Now, this is the absolute maximum, this is the absolute minimum? I have no idea. I can't possibly know that. Well, it's negative, so. Never be fooled by that. I'm gonna have some fun with this. Let's suppose for a moment this is actually the negative. Let's suppose that. I'm gonna add 1,000,000 to this. Will that change anything I did? No, actually it won't. It'll still be the same point. But if I add 1,000,000 to this, won't this be an astronomically large number? Does that change whether it's a max or min based on its size? No, this is a max or min based on the constraint, not based on the size. This could be a max, this could be a min, I don't know. But you can't say because it's negative it is. No, because if you're going to use that reasoning, add a ridiculously large constant to this. Or if you thought that was a big number, then subtract a ridiculously large constant. That doesn't change the gradients. That doesn't change the answer. Not from that standpoint. Remember, it's the constraint that produced the answer, not. So, is this a max or min? I don't know. Pick any ordered pair that satisfies the constraint. Any ordered pair. All right, look at the constraint. Keep it simple. Can you think of do you see anything that satisfies this?
3, 0.
3, 0. I love that answer. Let's test 3, 0. By the way, what would be the other good choice? 0, 2. Yeah, and having said that, well, let's see. Let me try. X is 7, and then Y would be negative. Let's see, what fraction? People will do weird things like that. Like, why in the world would you make it challenging? Always pick zeros. Can I just test 0, 0? Why can't I test 0, 0? Well, it's not on the constraint. Sometimes the origin will be on the constraint. Then it's the ultimate no-brainer. That's what you should have tested. Most of the time it's not, but I can make one of the variables 0. So 3, 0 or 0, 2 would both be great points to check. So now what am I doing? F of 3, 0 is 18, which is greater than negative 144. By the way, what if I had done 0, 2? What would that have been? That would have been negative 16, which is, by the way, also, in fact, any ordered pair you picked that was on the constraint would have produced a value that was bigger than negative 144. So your conclusion? Minimum. By the way, and it's always absolute, there are no locals. When you use the extreme value theorem in Calc 1, there were no locals. You were finding an absolute maximum and or minimum, not a local one. Because when you're subject to a constraint, there's no in-betweens. I want the biggest or the smallest. That means that every other ordered pair, when I plug it into F, will give me a number that's larger than this. That's what that means. Any question on this? There's nothing about the algebra here that should trouble you, but it's all about the setup and understanding how to interpret what the heck I just set up. This was nice because the algebra was real simple. So let's do one that's a little bit more. I want to do a 3-variable problem now. All right, let's do. All right, I've got a plane Okay, so I want to give you an idea of what it is I'm going to ask you to do in a moment. I've got a plane. Can I draw this fairly easily? Yeah, it's not too terrible. My scale's going to be a little off, right? 4500, let's say that's right here. And then I have 030, that'd be a little bit shorter. Oops, sorry. And then 0018 would be a little bit shorter, so it's something like this. Everybody understand? So there's my plane as it cuts through the first octave. Okay, I have a plane cutting through the first octave. What I want to do is I want to use the XZ, YZ, and XY planes as boundaries, and I want to stay in the first octave. So I just cut through here. So the shape of the enclosed region is now a what? Three-dimensional. I just enclosed. I have a plane that's cutting through. The walls and the floor are also boundaries. Just remember? Nothing? Four-sided, three-dimensional shape?
Tetrahedron.
Tetrahedron, good. You saved them. I have a tetrahedron. I want to inscribe the biggest prism that I could possibly get in there. Okay? I want to inscribe the largest prism. I want to inscribe the largest box, in other words, rectangular box, prism. Now, can everybody understand? I'm cutting through, but the X, the Y, and the Z of my box probably aren't going to be equal, are they? It's definitely not going to be a cube. Why? Because this is 45 units out, that's 30 units out, that's 18 units out. So I want to inscribe, I don't know if you can see it, I'm not going to try to, well, maybe okay, you know. There's something in there that I'm going to put. I'm going to put a box in there. Okay. I'm bounded by the planes and by the plane that's cutting through. Now, can we all conceptualize what's going on there? Yeah, no one's going to guess an answer. So, the box that I'm putting in, okay, so I'm putting in a box now. Again, don't worry about scale. My box has, right, an X. Well, in this case, actually, the X would be, just probably put it this way. So if that's the origin, okay, then that's the X, that's the Y, and that's the Z. But it doesn't really matter where I put them, does it? So what am I doing here? I want to maximize X times Y times Z. I'm maximizing the volume of a box. You know, could I have a box that's paper thin? Sure, in every direction, but I don't want that box. I want the biggest box I can possibly come up with. So I want to maximize that. What is my constraint? That. So let's call this, if you will, f of x, y, z. Subject to, well, I have to be on that plane, so why don't I make that my g of x, y, z? And I'll go 2x plus 3y plus 5z minus 90. Now I have a problem where I have two three-dimensional functions, excuse me, two functions of three variables, so technically four-dimensional. My plane that is cutting through is now a level surface of this constraint. Before there were level curves. And now we're going to do the Lagrange multiply problem. It's going to be the same problem. It's going to be a little bit busier because I have more variables. But the way we set it up and the way we solve it will be exactly the same. Okay. So the gradient of f is
235.
I'm sorry, a little louder.
235.
The gradient of f. So how about yz, xz, so, or xy? Now, Jamie, the gradient of G. What's that?
2, 3, 5.
2, 3, 5. Okay, beautiful. You're just ahead of me, that's all. All right? So when I do my Lagrange multiplier now, I'm going to get yz equals lambda times 2, xz equals lambda times 3, and xy equals lambda times 5. Whew. This doesn't really look all that friendly, does it? Oh man, if I solve for lambda, then lambda equals 1/2 of yz, and then but no matter how I do it, I got too many variables, don't I? Can anybody think of something clever here? What I'm about to do actually is a ridiculously common step that you're going to find, usually on the 3 variable problems. Don't look at the right side, look at the left side. Let's make the left sides all the same. How do I make the left sides all the same? What should I multiply by?
X. Y.
Oh. Now, technically, can't my variables be 0? Yeah, but we're trying to maximize the volume, so can any of your variables be 0? No, that would be impossible. All your variables would have to be positive numbers. Now, why would I do such a crazy thing? Because now these are equal to each other. Now, I don't know if that makes my life easier yet, but it's got to be better than what it was. So the first one says, well, if lambda times this equals lambda times this equals lambda times this, and lambda can't be 0, can you conclude that 2x equals 3y equals 5z? If lambda cannot be 0, then that must be true. Oh, okay, well, gee, how's that going to help me? Oh, I don't know. I think I just made the algebra real easy about right now. Why don't I replace 3y with 2x? And why don't I also replace 5z with 2x? Okay, going back to my constraint, then what would that be? 2x plus 2x plus 2x equals 90. Does that make sense? Because we just figured out the relationship was 2x equals 3y equals 5z, and I have one of each in the problem. Awesome. So what does this give me for x? 2x plus 2x plus 2x equals 90, so 6x equals 90, so x is 15. Now, if 2x equals 3y, then y should be 2/3 of x. 10. If 2x equals 5z, then z should be 2/5 of x, which is 6. Do a quick check. 2 times 15 plus 3 times 10 plus 5 times 6, does that in fact equal 90? Yes, it does. So it appears that my dimensions are what? My dimensions are 15, 10, my dimensions. So you can say 15 by 10 by 6, but make sure you have the right numbers in the right place. Your answer is not a point in space. You're describing the dimensions of a box. A lot of times when we answer a question like this, we'll give an ordered triple. And there's nothing wrong with that, but I'm asking for the dimensions of a box. Would there be a point in space? Well, technically, the furthest point out, right? Remember my thing goes like this. The furthest point out here would actually be the ordered triple, 15, 10, 6. Oh, why? Because I am 6 units high, I am 10 units from there, and I'm 15 units from here. So I'm creating a box by going in every direction. Now, is it the maximum? Well, it should be, but I still need to test something. So, go back to your constraint. Pick any ordered triple that satisfies your constraint. Think zeros. What do you want to test?
4500.
How about 4500? Then what would the volume, by the way, this is volume, right? So then f of 4500 is obviously 0. What is our maximum volume, by the way? What actually is the volume? It's 15 times 10 times 6. So the volume, the maximum volume, we never really said it. We said the dimensions. So the max volume is 15 times 10 times 6, which would be 900. So this number is less than 900. Obviously, 900 is the maximum volume, and it comes from 15 by 10 by 6. This wasn't that hard, was it? Now think about this. If you didn't have this, how would you do this? I mean, trial and error? Let me just find random dimensions, and first of all, come up with random dimensions and see if they're actually inside the thing. And no, that's not a way of doing anything. That's kind of cool. We just, this wasn't hard because the nature of the functions was fairly low level. All right. Let's do another one. This is a problem that I like to do in Calc 1. I'm going to go back to Calc 1 for a moment because it's a problem that, it's not a common problem, but it's one of these where you're not exactly sure what you're supposed to do. All right. All right. All of you went to kindergarten, correct? Everybody here was in kindergarten at one point. Hopefully not recently. All right, I was parent helper many, many times in my kids' schools. So here was a typical assignment. Do you remember the big construction paper you used to use? It was so awesome. You had this colored paper, it was huge, it wasn't flimsy. And so every kid got a piece of construction paper and you had to construct the box, an open box. I kid you not, they did this in kindergarten. And the teacher would ask me, well, how are we supposed to do this? I was looking this up in the thing. It's easy. Like this. I'd actually explain it to them. We're going to do this in a moment from a calculus standpoint. I was the only calculus parent helper, so all the kindergartners by the end could actually do maximization and minimization problems. I just created an open box from a piece of paper. You with me? So the question is, if I gave you the piece of paper, could you construct the open box with the maximum volume? And what does it all depend on? Once you're given the piece of paper, you can't say it depends on the size of the paper anymore. No, it depends on the size of what? The cuts. If I make the cuts too big, I pretty much will eliminate all the paper, won't I? Okay, this is a problem. I do this problem in Calc 1, and I actually, I give them all a big piece of construction paper, and they have fun, and you get to color it at the end. And that's the best part, right? All right, so I'm going to give you a big piece of paper. The dimensions aren't really that important. It's the concept of how I do this, because I want to be able to do this in 3D. So let's say it's 30 centimeters by 20 centimeters. Let's actually give it some length there. That's way bigger than 30 by 20, I know. I want to find the open box with maximum volume. Now, why an open box? Well, because you just saw I don't have a lid. I can't do it with a lid. I've asked you very similar questions on the last two quizzes, as you've noticed. I've asked you to construct, things involving boxes, and we did cost and stuff. It's not that different of a concept. So the first thing you all know to do is, I need to make cuts. Now tell me something about the cuts. Let's make that one there and that one there, right? Will that work? Tell me about my little squares. They kind of have to be the same, won't they? Yeah. Otherwise, when I go to do the fold, that won't work. So I think we all realize the cuts have to be exactly the same. All right, what do you want to call the cut? I don't know. How about, let's call the cut x by x. So now, when I do my fold, does everybody see my fold will be along the dotted lines? I would like to know the volume of the box that I just created just now. Well, what is it from here to here?
30 minus 2x.
30 minus 2x, good, because I had 2 cuts. Aha! And what is it from here to here? 20 minus 2x on the outside. So is it correct to say the volume of my box as a function of x would be base times height, or I should give length times width times height, however you want to say it. Do you agree with that? Are there constraints on x? Can x be any real number? I could mess it up, and by the way, in case you're wondering, yes, there were kindergartners who made their cuts too big, and when they're all done, there was no box because they just eliminated all the, literally I cut it in half and go, okay, that's not going to work. Do you all agree that negative volume is probably not a good thing? Okay, so x can be as big as 15? No. X is kind of have to stay between 0 and 10. Because once I make x 10, I don't have anything left on it. So clearly, I think we agree that x has got to be between 0 and 10. Why is that important? Because in the end, I can use extreme value theorem. I'm going to take a derivative set equal to 0, solve for x, and I can do a second derivative, I can do a first derivative test, or I can just check the endpoints. Here's the beautiful thing about checking the endpoints. We know the endpoints are going to give us a volume of 0. Therefore, whatever I get is going to have to be my answer, but we can actually prove it. Not just, it has to be the answer. That's not really mathematical. Who can yell the loudest? We proved it. Okay, so what am I going to do? Well, there's a couple ways I can go about it, but I got to take the derivative of this. I have a product of 3 functions. Do you really want to do a 3-way product rule? Please tell me you don't want to do that. No, you can. Why would you do that? No, what should I do? Multiply it. Multiply it out first. It's going to be a cubic, but multiply it out. All right, so I'm going to get 600 times x. Then negative 60, negative 40, that's negative 100x times x. Plus 4x squared times x. Yeah, it's actually that easy. This is volume as a function of x. Now, what's interesting is this is a cubic, so it's going to probably change directions all over the place. What's v prime of x?
600 minus 200x plus 12x.
Now, I don't think this is going to factor very nicely, but we can just use our quadratic formula, can't we? So, if I just use my quadratic formula, it might factor. But I doubt it does. I just made up the numbers. So what's x equal? 200 plus or minus, right, 200 squared minus what? So 600 times 4 times 12. So let me write this out. 200 squared, that'll look all right. 40,000 minus 28,800 all over 24. Does that look right? Well, that's square root of 11200, which is really big. Does anybody have a calculator that reduces roots easily? I'd rather have that reduced. Yeah, I can do it by hand, but
That's 40 root 7.
that's 40 root 7? Oh, I like that. So I have 200 plus or minus 40 root 7 over 24. Now, does that look correct? I have 2 answers. Huh. I can reduce this and give you the answer as fraction plus or minus fraction times root. And for a group of kindergartners, that's exactly what they need. Would it be okay to give a decimal value here? Because I'm using a ruler and measuring. What do you think? Let's give a couple decimal values because I need to know that my answers are actually reasonable. So let's do the plus. 200 plus. This is approximately 12.74. And then I do the 200 minus and I get it's approximately 3.93. Does anybody else get those numbers? Okay. But I got two answers. Did I get two answers? No, what do we call the bigger one? There's actually a term mathematically used. It is a solution to the equation, but it's not a solution to the problem. So it's called extraneous. I have an extraneous solution. Again, I solved the derivative equals 0. It is one of the solutions to the derivative equals 0, but it's not in the domain, which is why I tell people in Calc 1, the first thing you do in every problem in Calc 1 is identify the domain, because otherwise you can give answers outside the domain. We were about to give an answer that was actually not possible. But it solved the problem, but it was outside the domain of what we said was reasonable. So basically my cuts are going to be pretty close to 4 centimeters. Do you agree? That will maximize the volume of my box. That was nice. Okay, so now let me change it on you a little bit. I want to make it a little bit more challenging of a problem, but understanding the reason this worked was because it was an open box. By the way, you notice I didn't start with a square. I purposely started with something that was not square because that would have made it a little bit too simple if I started with a square. It may or may not have worked so nicely. So let's change it a little bit. I now want to do a closed box, which means I'm going to have more variables going on. Now, okay, same problem, almost the same problem. I want to find the dimensions of the open box again. With maximum volume. Didn't we just do that? We just did that. And I'm going to give you a piece of paper. Constructed from a piece of cardboard, or, you know, because we call that construction paper, right? It was not quite cardboard, but it was, you know, sturdy. A piece of I'll call it cardboard this time. This is almost exactly the same as last one. Last problem, by the way, it was 600, wasn't it? It was 200. It was 20 times 30. We just did a problem from Calc 1, technically a problem from kindergarten, where I gave you a piece of construction paper of 600 square centimeters, and you just concluded exactly what to do. By the way, all I did was tell you the cut. So when I go back and do the dimensions, obviously one of the dimensions is, or was what? It was 15 minus 2 times this, and the other one was,
It was 30.
I'm sorry, 30 minus 2 times this, and the other one was 20 minus 2 times this. So those would be the dimensions. That was the size of the cut. This is almost the same problem. It's almost the same problem, except I didn't tell you the size. I didn't tell you the dimensions of the paper. Why? Because all I'm telling you now is how much square footage. That's kind of like the question I asked you earlier. I'm going to give you a tile floor, and I'm going to give you 4,800 one-by-one tiles. I want you to construct something, but I'm not going to tell you the dimensions. You're going to tell me the dimensions. Oh, so I'm giving you 4,800 square centimeters. I'm giving you the area. When you are, let's say you're going to build something. You're going to build a house. You can build whatever. And you've budgeted for certain things. A typical scenario is, you know, you're building the perfect family room, okay? And you decide, I want it to be 1,000 square feet. It's a big family room. Great. And you figure out the material costs and all that stuff. By the way, what are the dimensions of your 1,000 square feet family room? What exactly are the dimensions? Well, aren't there an infinite number of possibilities that, yeah, I only told you the square footage. You would figure out the dimensions that would maximize the area. No, you're given the area. Probably minimize the cost. Oh, okay, so probably closer to square may do it. But, you know, I might be open at one end. I might have a heavy wall here. There's different things. One of the questions on one of your new quizzes, I said, consider construction where the walls are cheaper than the floor and the ceiling. You know, now I want to maximize based on these restrictions. So in this case here, I want to maximize volume based on this, but I didn't tell you the original dimensions. Oh, so sort of like I'm giving you all the tiles and you're going to figure it out. So how does this change things? Well, I still have a box. Okay, so let's do our box. I have a box without a lid. That makes it a little bit easier, I guess. But isn't it still going to be, you know, actually, it doesn't matter which one. Oh, it doesn't matter which one. I'm not putting it on the XYZ anymore. Okay, so I have XYZ. Maybe maybe the trickiest part of this problem is stating what the constraint is. What is the constraint? Okay. I've given you the materials. You're going to construct this room. Don't worry about the ceiling. Somebody else is going to do the ceiling. You're going to put the floor and the walls together. And I've given you the materials. Right? How many things do you have to consider? Well, you have a floor. You have those two walls. You have those two walls. Are any of them squares, first of all? No. Are those walls and those walls, is that wall the same as that wall in terms of size? No. Are any of them the same as the floor? No. Oh, do I have some sameness? Well, yeah, those walls are the same. Those walls are the same. Floor and ceiling would be the same, except I only want the floor. I've just told you how to figure it out. First of all, what's the area of the floor?
2xe.
What's the front wall?
xe.
How many of them are there?
2.
2. What are the side walls?
yz.
YZ, how many?
2.
Does that make sense to everybody, what I just did? I just figured out the total what?
Area.
Surface area. Okay, we didn't think about that. In 3 dimensions, so surface area, because I have multiple phases here. And what must this be?
4,800.
That's why I said this may be the trickiest part of the problem, is figuring out how to state that. You go, okay, now, if it were an enclosed box, what would be different? And if it was an enclosed box, do you already know what the answer would be? Yeah, it'd be a cube. That's why I didn't do a closed box. It's too easy. If it were a closed box, you would maximize volume with a cube the same way in 2 dimensions you maximized area with a square. Not because I'm telling you that's what you would have discovered had you done the problem. That's boring. Is it going to be a cube? No. But it's probably reasonable that my base may end up being a square. That's probably reasonable, because long and skinny wouldn't be as much. So if I find out at the end of this problem that my base ends up being a square, I won't be surprised. Here's what you cannot do. You cannot start by assuming. And a lot of people make this mistake. They start by assuming squares somewhere along the line. No, don't do that. Let the results dictate that. If you start by assuming that, you may not be correct. And I'll give you a simple example. We want to construct this room. We're on the 4th floor. Is there a lot above us? No, but what if we were on the 1st floor? There's a lot above us. Okay? You have what are called load-bearing walls. If I remove this wall right here, what will happen? Nothing, actually. Nothing. It's not a load-bearing wall, it's a partition. And what I mean by that is, if I remove most of these walls, by the way, when this building was constructed, these were the last things put in, just so you know. They're partitions. They might as well be made of, what's the old Japanese tea houses, right? Paper. They do absolutely nothing. Could you punch a hole in them? Yeah, if you just hit it really hard. You don't do anything. But what about those walls? Those are load bearing. They get some big old nasty beefy beams holding those ones up. This one here, partition again. So you have walls that are very, very heavy duty because they got to hold up certain things, and there are other walls that don't do anything. They're just separators. I'll give you a simple example. How many have ever been to Vegas? You ever been to the hotels in Vegas? Okay, I used to compete years and years ago, and Vegas had some of the best international tournaments. And they would be in the hotels. They'd always be on the bottom floor of a hotel. You go to the bottom floor of a hotel, and it's always changing. They put in walls, they put in partitions. But the bottom floor of a hotel sometimes is as big as a football field, which brings up a question I always talk about in Calc 1. You got a 20-story hotel, and you have an area literally a football field size, and there's no beams anywhere. It's like, how is the upstairs staying, well, upstairs? That's always a great question, you know, because the construction is actually brilliantly designed. But what they'll often do is they'll put in partitions to section things off for whatever events are going on. Maybe several people wanted to use that bottom floor of the hotel at the same time, but they don't have large parties, they just put in partitions. Those partitions don't do anything except separate. But there are certain walls that have to hold the building up because they have beams. So my point being, the cost of that wall isn't even related to the cost of that wall, which means it would be impossible to maximize efficiency or minimize cost by making any part of this a square. A lot of people just automatically say, well, you know, you gotta have squares. Actually, tell me how many of these rooms in this building are square anywhere. You're not gonna find a single square anywhere in this building, because that wasn't the most efficient shape to, see, they started with, we have this much money, what do we want to maximize? The space. If I give you the money and you're maximizing the space, there's gonna be certain things you do differently, because you gotta have certain things in place, so we made the rooms a certain size. It was all based on maximum efficiency. Just so you know, they did a lot of consulting with the math department when they designed this building. Otherwise, if we weren't careful, this room may be really long and narrow, or worse, this way, you know. So this is the situation. It doesn't change my big picture if I put the roof. We just know, we have a feel it would end up being a cube. Why? Because if I think of this in terms of construction costs, I'm saying the floor and the walls all cost the same per square foot. And in real life, that would be utterly impossible. In fact, the bottom floor, oh my goodness. The bottom floor, the floor would be so unbelievably expensive that you would not even believe it. So, well, what about the other floors? Because of the cement. Oh my God, the rebar, the construction, how deep they have to go. That bottom floor costs so much money. Way more than all the other floors. Because it's got to support the entire building. Each floor here doesn't have to support the building, it just has to support these beams. So, I'm going to let G of X, Y, Z. So, give you a quick lesson on construction, because I want you to understand the math we're doing right now is the only math that exists in real life construction problems to answer the question. There is no other version that you can do if you were actually trying to maximize or minimize. Now, when you're building your house, do you think about it that way? Maybe or maybe not, but what if you have a budget? Then you have to think about it, don't you? See, this is the person who has a budget. They have to think about these things. If you don't have a budget, then it may not matter. So this will be xy plus 2xz. That's why sometimes I really love this type of math, because it's real life and you can answer questions that you didn't even realize were there. So this is my problem. This shouldn't be terribly different from the last one, should it? Because why? I don't have any exponents. That definitely makes some of the stuff a little bit easier. So if I call this, again, just generically, let's call this your f of x, y, z, just so I can keep the same notation. Then the gradient of f is yz, xz, and xy. Yeah, we just did a version of this. And the gradient of g is
y plus 2z.
So y plus 2z. Be really careful.
X plus 2z. 2x plus 2y.
Everybody okay with that? Make sure we got, yep, okay. Wow. All right. This one is probably a little trickier than the last one. So when I set up using my Lagrange multiplier, by the way, it is absolutely correct to write gradient of f equals lambda times gradient of g and then proceed. But since you've already expressed the gradient of f and gradient of g, you can go directly to the three equations that that produces. Everybody understand? It is correct to start by saying, all right, now the next thing I'm going to write is this, and then physically put a lambda in front, and then distribute the lambda, and then set up your equations. But I don't know. I think some of that's a little unnecessary. What are my three sets of equations then? Equals lambda times this. Yeah, I can go. You can go directly to this at this point, but always start with these. You got to state these, otherwise there's no equations to be had. And then xz equals lambda times x plus 2z, and then what is the last one? Xy equals lambda times 2x plus 2y. So, like before, perhaps it would be efficient to make the left sides all equal. Okay, you guys want to do that? If I make the left sides, let's see, let me do this. Like before, if we do this, then I can equate the right sides. Okay? So if I equate the right sides, what do I got?
X, Y, Z.
Well, I've got, so the left sides are all the same, so the right sides are now, I'm going to just write it out. I'm not going to do anything yet. Here's what I got. Boy, that looks so busy, except that lambda cannot be 0. So can I just remove the lambda from these three? Yeah. Because lambda cannot be 0, so y plus 2z times x equals x plus 2z times y equals 2x plus 2y times z. That's so busy. What do you think? Maybe distribute? You guys want to distribute maybe? So if I distribute, I've got xy plus 2xz equals xy plus 2yz equals 2xz plus 2yz. Do you see some of the same terms showing up? In the first two, what do you notice? They both have an xy. In the last two, you notice they both have a 2yz. And the first and last have a 2xz. So perhaps I can do some form of manipulation with these. Now, if I go back to here, though, it might even be easier. Stare at this for a moment. Like for example, see this? That's exactly this. Oh. So maybe I can replace that with one of these or something of that nature. What do you think? Is that's in the problem? This is also in the problem, the entire thing, and oh, by the way, this entire thing is also in the problem. Does everyone see that? So what I can do is I can equate, I can separate it. There's more than one correct way I could do this. Okay? So if I put all these together, what will I get? If I put all these together. Well, let's put the first two together. Again, do we agree that x, y, and z cannot be 0? We're maximizing the volume, so 0 is not a possibility. Why is that important? Because in this equation here, what does that say? Doesn't this say that 2xz equals 2yz? And if none of the variables can be 0, doesn't this mean then that x equals y? Oh, now let's put the, how about if we put, let's see, will these two together work? If I put these, let's see, no, maybe I don't want to put those two, let's see. Actually, I can put any of these together at this point. But with that, let's say I put x equals y. So what I want to do is rewrite these guys, either all in terms of x's or all in terms of y's, one or the other, it doesn't matter. But if x equals y, let's say we make everything now x's. So what's the first one now say? If x equals y, then I have x squared plus 2xz equals. X equals y, so x squared plus 2xz. Okay, that's, I already know that. And then what's the third one say? 2xz plus, we're replacing y's with x's. 2xz. Ah, so those are already equal. So now what have we got? X squared equals 2xz. From probably shouldn't say this, but from Animal House. You guys remember Animal House? You guys never saw it? Oh my gosh, if you're in college, you have to see that. That's part of the college initiation. But Dean Wormer, when he's talking to the students, he says, "Fat, drunk, and stupid is no way to go through life, son." It's one of my all-time favorite lines, is he's, trying to be thoughtful to the, the frat boy. Kind of what. It's one thing to let everyone else know your conversations, but when your conversations sound like a bunch of third graders, it's worse. What can I take from here if the variables cannot be zero? What can I factor this?
X equals 2z.
X equals 2z. Is that important? Yeah, we just, by the way, this was not trivial by any stretch. But we were able to figure it out. We have x equals y equals 2z. Now, how am I going to figure out the values? That's where I go back to the constraint and pick which variable you want everything to be in terms of. It does not matter because each statement has an x or a y or a 2z in it. So does that make sense? It doesn't matter. I think it's, whatever is more comfortable. So let's say we're going to go back and it's not this. I needed this in order to take a gradient, but this is what I actually used to solve because this is an equation. So let's replace y with x and let's replace 2z with x in this equation. How's that? If I do that, what will I get?
X squared
I'll get x squared
plus x squared
because that's 2z, so plus x squared.
plus x squared.
Oh my goodness, are you serious? Yeah, came out that nice. Oh, that's wonderful. So that gives me 3x squared is 4,800. So what does that make x? Use your calculator if you have.
40.
Well, it'd be technically plus or minus 40, except that x is the dimension, so the negative is extraneous, isn't it?
What did you substitute to get the x squared?
Right.
Okay.
So I replaced y with x and I replaced 2z with x. That's important, the 2z with x. Because there was no top. So this says that x must be 40. So if x is 40, what's the y?
40.
What's the z?
80.
Are you sure?
20.
20. X equals 2 times z. Okay. Now, did we say we suspected the floor might be square? Because I did not give you a cost. I didn't say the cost was different. I just said there was no roof. By not having a roof, think about it in terms of materials. I'm giving you, think of this as 4,800 feet of plywood. And you're going to make the thing. Well, if I got to use a whole bunch of stuff for the roof, doesn't that make the whole thing smaller? I mean, it would be a cube, but it'd be way smaller. But if I don't have to have a roof, I can go way wider, way bigger. And that's what we just did. We figured out the base was 40 by 40 and the height was 20. Now, we believe that maximizes the volume. It does, but how do I now show this? Take anything that satisfies the constraint. Oh, that constraint is tricky. Well, how about if I use some zeros? For example, what if I use, let's see,
X equals 800, y equals 1, equals 0.
let's see. Remember, it's got to satisfy the constraint. I actually can't use zeros, can I? Because if x or y is 0, if x is 0, well, I guess technically, yeah, I could do that. I could say, well, that would be really boring. I could say x is 0. How about y is?
0. Oh, wait.
No, because if x is 0 and y is 0, then all three of these are 0. Let's make
1.
y be 1. Okay, I like that. X is 0 and y is 1. So we have 0, 0, 2 times. So z would be 2400. Yeah, I can't make 2 of them 0 because then that won't work. Now, what is our volume in this case? Our volume would be 0 times 1 times 2400, which is 0. And what is our current volume? 40 times 40 times 20. That's 32,000. I think that wins. Okay? But I still have to test it, and that's my test point. So the volume for this dimension would be 0. The volume for our answer was 32,000. Yeah, I'm pretty sure our answer is correct. Wow. Now, the key is not the algebra. The key is the setup. This is not trivial. This is harder than most problems because the nature of this. But once we figured out, oh my goodness, when we start manipulating it, things usually fall into our lap kind of nicely. Okay? Question. Okay, I want to do one more. All right, so let's suppose. He's dead. He's dying. Let's suppose we have an ellipsoid. X squared plus y squared plus 4z squared. And let's just pick a random value. Let's say, I don't know, 36. Okay. We often just generically refer to this as an ellipsoid. Mathematically, this is, of course, an A. Okay? It's circular in the xy, it's elliptical in the xz and yz. So technically it's called a circular ellipsoid. What if none of my coefficients are the same? Then we just say ellipsoid. You don't say elliptical ellipsoid. That'd be like calling a sphere, no joke, a circular circuloid. I've actually had people tell me that. Like, that's really weird. This is an A, okay? How many have ever seen the ships, the model ship put inside a bottle? How many have ever seen one of those? Unbelievable. And the person's, crafting this through the narrow opening. You've got the bottle, right? And you're building a ship on the inside. What's the biggest ship you could possibly build? Well, one that's touching all the walls and the sides. That's called inscribing. I want to inscribe a prism into this. A prism, that tells you something. That means it's got to be rectangular in nature, not pyramid or anything like that. I want to inscribe a prism into this. And I want it to be the biggest prism. There's an infinite number of prisms I could do, but I want the biggest one of all. How would I do that? So it's kind of like saying, I have something like this, and I want to put inside, Now the rules on inscribing, it means that all of the vertices of my prism have to touch. Okay? They have to touch. I'm going to give you a simple two-dimensional example because this is not something a lot of you are familiar with, the geometry part. So, I want to place a rectangle inside this. Do you agree there's an infinite number of pictures I could draw? But if I said I wanted to inscribe a rectangle, what changes?
It's the shape like that. The size of the circle.
Well, in other words, I got to do something like this. To inscribe means all the vertices have to actually be touching the circle. If I just said put a rectangle inside the circle, I could make it small, I could make it large, just can't exceed the circle. But this would be the inscribed rectangle. That's the difference between inscribing. If I started with the rectangle and I said draw the smallest circle that touches the rectangle, there's a different word. I'm starting with the rectangle and I'm putting the circle around it. Does anybody know what the word we use instead?
Circumscribed?
Circumscribed. Inscribe means you're putting inside. Circum literally means around. And people say, really? Remember we talked about our Latin prefixes? That's a really important math one. You want to sail around the world? What's that called?
Circumnavigate.
Circumnavigate the globe. Oh, okay. It's like, really? Yeah, that's it. That's where the circum comes from. What do we call the distance all the way around a circle? Circumference. Circum means around. So I started with the rectangle and I want to put the circle around it, but aren't there an infinite number of circles I could put around it? Yeah, but only one would touch the vertices. That's called the circumscribed circle. So depending which one's put first. If I'm putting it inside, it's inscribed. If I'm putting it on the outside, it's circumscribed. That's it. So I am inscribing this. So I am inscribing a three-dimensional shape in here. Yikes. Oof. So how do we do this? Well, I got to figure out what the dimensions look like. Well, would you say this is centered at the origin?
No.
Yeah, it's not x minus something. So if it were x minus something squared, y minus something squared, z minus something squared, then that's where it would be centered. Think of it as x minus 0, y minus 0, z minus 0. Yeah, this is centered at the origin. If it weren't, this problem would be extremely difficult. But because it's centered at the origin, then I'm suspecting, right, that whatever this ends up looking like, you know, this thing here is also going to be centered at the origin. You know, the origin is going to be dead center, which means that left, right, up, down, I should be going up and down the exact same amount. I should be going left and right the same amount. If I call x comma y comma z the coordinate in the first octant that vertex is, then wouldn't this way be an x negative y z, and this way would be x y negative z, and this, does everybody see that? Oh, so what would the dimensions be? This is not a trick question. If I'm going x in that direction, then you'd say negative x that way, 2x. Does that make sense? If I said I want to inscribe the largest prism, but the prism's going to remain entirely in the first octant. We did a problem like that earlier. Oh, now I'd be bound x equals, I would have x and I'd be bound by 0. Y, 0. Z, 0. Then it would just be x, y, z. Why? Because I'm bounded by zeros on the other side. But this is x to negative x. This is z to negative z. Y to negative y. That's okay. So I want to maximize this subject to this. Now, is that harder? Is that easier? About the same as what we just did? I think this one might be a little bit simpler because, again, all the degrees are the same and the partials are just, it's not that terrible. Okay? So I'm purposely not going to finish this problem because I've asked you a similar question. But I want to help you set it up because I get a lot of questions about the setup. So I want to maximize, let's call it f. But what am I maximizing now? Am I maximizing x, y, z? Maximizing 2x, 2y, 2z, which would be, if you're maximizing x, y, z, you will get the wrong answer. You won't even be relatively close. Okay, don't want to maximize x, y, z. You want to maximize that, which is what? 8 x, y, z, yeah. In other words, if you maximize x, y, z, you're going to have an answer that's 1/8 the size of what it should be. And that means when you go to prove it's the maximum, if you use any point that didn't have zeros, you'll get the wrong conclusion. Ooh, here's a situation where I could actually get the wrong answer because I did a wrong setup. Yeah, that 8's actually really important in the final run. Subject to, let's call it g of x, y, z equals what? X squared plus y squared plus 4z squared minus 36. Why did I make it a 4z squared? What if we just left it as z squared? What if it were x squared plus y squared plus z squared? This is not, I don't even need you to use math. I need you to use recent history and a little common sense. If I make it x squared plus y squared plus z squared equals 36, isn't that a sphere? And I want to maximize the volume of a prism placed inside a sphere. What's the prism going to be? It's going to be a cube. Yeah, I mean, you already, without proving it, you already have a feel that that's what it's going to be, and it's actually a simple proof. It'd be a really, really, really easy problem, because think of your partial derivatives. They'd all have the exact same coefficients, and yeah, that problem is boring. It's not going to be a cube. I don't want it to be a cube. But if I make all three of these coefficients different, the algebra required to solve this actually gets kind of icky. There's a lot more going on, and it's not as clean. You can still do it. You have all the tools to do it. It's just the answer will not look as nice, and it won't be as friendly. So I want to do this. So when we set up our gradients, and we set people to each other, we should get a set of things that we're used to. We're going to have an xz, a yz, an xy, and oh yeah, let's do the same sorts of things we just did. It works beautifully. But I'm going to leave you with this one. So Lagrange multipliers, they're an application to find extrema. Let me throw a what if at you. What if we did a problem and we actually came up with two answers? It'd actually be a lot of work for me. I can do it, but it's a lot of work to come up with a problem with two answers. Usually you're only going to get one. But if I got two answers, and let's say the first answer produced a functional value of 100, and the second one produced a functional value of, I don't know, 5. Do I have to do a test? No. The 100 would be the absolute maximum and the 5 would be the absolute minimum. How do I know that? Because 100 is bigger than 5. And the absolute maximum has to be bigger than any point you test. How does 5 have to be the absolute minimum? Because it's smaller than 100 and it has to be smaller than every point you test. When you get two solutions, you don't actually have to test. The bigger one's absolutely the maximum, the smaller one's absolutely the minimum. Why? Because every other point had to be different from them, so every other point would fall somewhere between them, by the way. You couldn't have something lower than your minimum. Because if you had something lower than the minimum, then the minimum would have had to be the maximum, but the maximum was the maximum, and well, all hell breaks loose. Right? Dogs sleeping with cats, and it's bad. If you get lucky enough to have one with two solutions, you got to do a few problems, but you know, every textbook printed has a whole section of these, and the problems will look very much like what we just got done doing all day, okay? And it's good stuff. Now, where we are, we have one section left. We are completely finished with every conceivable application of the derivative you're ever going to see the rest of your life in a calculus context. The next thing we're going to do is start the integration, okay? So the next few weeks is going to be about integration and applications of the integral in 3D. But if you can differentiate in 3D, integrations, it's not really that much different. If you think of a partial derivative, then think of like a partial integral. It's going to be very, very similar, and it's going to make perfect sense. And we're only going to do the intro to integration. We're not going to get very far into it. So Monday's lecture is the last lecture of new material. I will go ahead and post the practice test. Now, if I don't post it, people send me emails saying, can you post it early? I want to start review. So I always just go ahead and post it early. It would be wise to take a look at it. Obviously, there's going to be integration questions at the end that you haven't seen yet, so don't worry about it. The exam, I think, is still 2 weeks away, but you know, might as well get a little bit of a head start, okay? Let me go ahead and stop there.